Now that we've introduced the modulus argument form, I want to talk about why it's so important. Firstly, its consequences in multiplication and division of complex numbers, as well as geometrically what they look like. Now, to begin with, let's say if we had z1, the first complex number, having a modulus of r1 and an argument of theta, and the second complex number, z2, having r2 cis phi. To multiply them, we simply multiply the moduluses and add the arguments. To repeat that, we multiply the moduluses and add the arguments. You can prove that as an exercise of your own by simply multiplying these out carefully and doing a bit of trig identities. Right, now what does it look like on the Argand diagram? Let's say if we started off with z1 equals to r1 cis theta. And I'm just demonstrating it here, that's z1. Okay, and we know its argument is theta. Now, by multiplying it by z2, we have transformed the modulus by a magnitude of r2. So let's just say, for 10 in this case, that r2 is greater than 1. So z1 is going to become longer, as we can see in this particular vector. Also, the original z1 is rotated anti-clockwise by the argument of z2, as in phi. As you can see, this is a rotation by phi anti-clockwise of the original vector. So the new vector is not only lengthened by the modulus of z2, it's also been rotated by the argument of z2. Now here are some basic results that follows from this. Let's just say we want to multiply z, any z, let's just say this one, by the complex number I. Now it happens to be that I is a really simple complex number, which is 1 cis pi on 2. We can easily quite see why, because I has a modulus of 1, and because it's on the complex number plane up in the y-axis, it's got a modulus of pi on 2. So what we actually do here is, because we're multiplying by 1 cis pi on 2, our modulus hasn't changed, but our argument has increased by pi on 2 radians, which is just simply a 90-degree rotation anti-clockwise of the original z. So that one is going to be zi, okay, 90-degree rotation. Well, now what about z bar? Z bar is quite simple, because what actually happens is that if you had z as originally being r cis theta, then z bar would be, you see, if we got cos theta plus I sine theta as z with an r outside, and we transformed it to r cos theta minus I sine theta as its conjugate, then the only thing that has really changed is the second term in the brackets. But you know what? Because of cos, the cos relation, you can say that's cos negative theta plus I sine negative theta. So I've incorporated this negative sign into the sine theta, and I can just make up a negative sign here anyway because they're the same. Okay, and what this really is r cis minus theta. So the conjugate of z is simply the reflection of z about the real axis. So this will be the conjugate of z, because we're going minus theta instead of theta. Okay, so that would be theta, but obviously in the wrong direction, in the negative direction. Okay, what about 1 over theta? 1 over z. 1 over z is a little bit more difficult because it really depends on the modulus of z. Now let's just say, in this example, let's assume that the modulus of z in this case is currently greater than 1. So by doing 1 over z, okay, we're going to actually have 1 over r, and because we're doing some sort of division, we're going to go cis negative theta. Okay, because dividing is like the opposite of multiplying, and we're going to actually minus the angle. I should have probably written that up on the top as well. Okay, I'll write that a bit in a second. So what actually happens is, yes, the argument is still negative theta, so it's almost like a reflection, again, but the difference is that the modulus changes based on the original modulus, right? Because we're talking about the reciprocal of the original modulus, and it could be shorter or longer depending on whether the original modulus is greater than 1 or not. If it was equals to 1, then it would have been the same, and what actually happens is that if the modulus of z equals to 1, then the conjugate of z is actually the exact same as the reciprocal of z. And that's actually a really useful result to remember, if the modulus of z is 1. Okay, now since we were just touching on the idea of division, I might as well add to the top of the page, the division version of this. Okay, it's simply divide the moduluses and subtract the arguments. I'll put a box around that as well. Now the proof of this isn't so easy because we haven't quite learned the de Moivre's theorem, where we can deal with 1 over z2 as if it was just a transformation of z yet. So we'll deal with that later. Okay, now the last example and the easiest one would have simply been if we had z like this, okay, and we decided to do minus z, in other words minus 1 times z. This is simply a 180 rotation. Okay, this is sort of like saying z multiplied by minus 1, which is like z multiplied by cos plus I sine of pi. Okay, and that's just a 180 rotation, or in other words, just a negative version. So that's minus z. Very simple. Okay, now we want to talk about this thing called de Moivre's theorem. De Moivre's theorem is more often used in dealing with solutions to polynomials and the roots of unity, but let's not get too bogged down on those other things and just concentrate on what we can get out of de Moivre's theorem at the moment. So at this point, we've discovered that multiplying means multiplying the moduluses and adding the arguments. So just pretend if you were just multiplying 2 of these together. First, you might notice that these have a modulus of 1, so we don't have to worry about the modulus at all. But what actually happens is that if you multiply 2 of these together, you're adding them arguments, so you're really getting cos 2 theta plus I sine 2 theta, right? And you can obviously see the pattern here. If we multiply by another one of these, we're going to get 3 theta, 4 theta, and so on. And that's where the theorem, de Moivre's theorem, comes in. Okay, it's a fairly simple consequence of the multiplication of mod arg form. Right, we have enough information now to attempt the questions at the end of this video.